Thank you very much. Appreciate the opportunity to speak to you today. I am exhibiting out there. If you want to see the deck scanner I'm showing, we do have it at the end of the hall. So, having said that, let's get started. So, I'm not sure how many of you know stress waves, but I put up a basic slide. So a compression wave, a primary wave, is the one we're speaking with, a sound wave. It's the fastest in concrete, typically 12 to 15,000 feet per second, a relative velocity of 1, say, for this discussion. So when an impact is applied, is there a pointer? Okay. This is the fastest wave, and it's a push-pull wave. The second wave from an impact is the secondary wave or shear wave. It has a shearing action. Only 7% of the energy is a primary compressional wave. 26% is a shear wave, and 2/3 of the energy is a Rayleigh wave or surface wave with a rolling motion, rolls backward as it propagates. They're all related, but in terms of the velocities, Young's modulus, Poisson's ratio to each other, and so you can calculate these different things. And Young's modulus is 2 times the shear modulus times 1 plus the Poisson's ratio. So the point of this is all low strain, very low strains in the non-destructive testing. So there's a report I wanted to bring to your attention. A number of people were involved in this, a number of vendors. It was done recently, published this summer. You can get it online. I gave a link. The Indiana DOT and Purdue University combined to do this long-term project and network level NDT implementation plan for Indiana. And that just shows here the report cover, the authors of Gia Williams, Ba, and Mark Bowman at Purdue University. So 9 consultants at NDOT did NDT of concrete bridge ducts in the fall of 2020 and the summer of 2021. It was done with ground penetrating radar, both air-launched and ground-coupled, both network level and project level. The automated sounding was done on a network and project level. Impact echo scanning was done on a project level. We were involved in that along with NDOT. The infrared thermography was done with aerial, vehicle, and pole-mounted network and project level. And they had a limited number of concrete core comparisons to check for delaminations and soundness of decks. So it's a very comprehensive study. This is just showing on the cover the impact echo scanning here and some of the decks. So some of the key findings are summarized here. First, the impact echo results compared reasonably well between the two entities, and they were repeatable. And cores, interestingly enough, universally confirmed the IE delamination results. It's unusual, but it worked out very well. It's a very direct test. So the infrared thermography was comparable between entities. So one of their purposes is to see how repeatable anything was for different groups to do the work. It was more affected by shaded deck areas. I thought previous presentation was excellent, very good. I hadn't seen bituminous work that well before. There were small temperature differences, but they were a little less than those found with impact echo, but greater than values from automated sounding. And they were dealing with bare concrete decks with various concrete overlays, no bituminous in their study. The ground penetrating radar was very good, excellent for rebar cover depth, but the bridge deck deterioration results were very much a lot of variations in values and locations. So they didn't want to recommend that as the sole method to evaluate bridge decks. But it was valuable for corrosion activity, more like corrosion potential, and it's useful when combined with other primary methods like impact echo or infrared thermography. Finally, automated sounding had low delamination values versus the other NDT methods. So going forward, what the report recommended is the following implementation plan. Aerial IRT was recommended for network level inspection for a large number of bridges, then followed up with a network level vehicle mounted, as was mentioned, problematic decks, and maybe along with air-launched GPR to complement the infrared thermography. Impact echo was recommended as a project level test for future NDT assessment to detect delamination, dust continuities in bridge decks requiring traffic control project level. And the pole-mounted IRT was recommended possibly as a secondary project level where you had a lot of traffic, and getting traffic control was difficult. So having said that, we'll get into the rest of the talk. These are 5 of the NDOT bridges that we studied along with NDOT in the state. This is, just to orient you, this is Indianapolis down here. So this is a deck scanner that we came up with. It came out of an NCHRB IDEA contract. It's slow rolling and walking, but very detailed testing. So you have these sensor wheels, and every 6 inches, if you're doing impact echo only, typically separated a foot, although you can go from 6 inches to 9 inches to 12 inches to 2 feet apart, pushing along, walking typically a mile an hour. You can also do surface waves with it, which I'll explain more when you line up the sensors. Looking at concrete and asphalt quality, cracking damage, slab and deck pavement thicknesses, and even elastic modulus for strength estimation, calibrated with cores. So a close-up of those sensor wheels is shown here. These are the solenoids with the displacement transducers with a thin urethane tire, if you will, that protects them as they're rolled along. They're spring-loaded, making good contact with these 20-pound wheels with the deck and sharply impacting it with the solenoids. So every 6 inches, as this is rolled, you get a test result on each of the 2 wheels. This shows both NDOT and ourselves doing scanning, walking the deck. Indiana DOT owns a couple of these systems. Iowa has one of them. I understand the Indiana DOT has done several hundred decks now. They're using it throughout the state when it's a project level approach. We also did ground-coupled GPR with a GSSI system. This is the SIR 4000 with a 1600 megahertz antenna for comparison. And both units had GPS mounted on them for precise location of the testing. So this slide came out of Sharp 2 research, FHWA, but it basically illustrates the principle of impact echo and why it does work well. It's a very direct test. There is an ASTM standard for the test, but the depth of the echo is equal to a shape factor, which is 0.96 on a slab, times the compression wave velocity divided by twice the frequency or resonant echo frequency. And it varies. It's a lower shape factor if you have multiple echoes, resonances in beams and column shapes. But in a slab, you have one main echo. So here's a thickness echo result. It's been impacted. This is shown as point by point. Obviously, without scanning, you can't do point by point testing easily on bridge decks. It takes forever. But here's an example of a tight crack with a bottom echo still present. And you can see cracks when you lose about 25% of the contact area, is what research showed by Carino and Sansaloni back in the day. You got here a bottom delamination where it's a deeper echo. And a top delamination shows up as a flexural resonance because it's that hollow drummy sound you hear when you do automated sounding or acoustic chain dragging. So here's an example of a scan line result. This is the distance scanned. This is the deck thickness. Probably a little hard to see, but that's 0 to 20 inches, nominally an 8-inch thick deck. And in this result, or 9-inch thick deck, you've got one signal here at this red cursor, and that's the frequency of it. The frequency of the echo then shows up nominally 9,000 hertz, corresponding to about 9 inches. That's a sound result. Some delamination areas are looking thicker in this scan. And that's what you're seeing, is the delaminations are these extra thick, low-frequency resonant echoes. So point-wise, these are all the tests on this particular deck, Bridge 24220, and you can see all the many points before any smoothing is done. And here's an echo depth scale from delaminations into the expected thickness range, into shallower echoes, indicating bottom steel cracking. Delamination. Here's smoothing of it, a little easier to look at instead of all the specific test points. But keep in mind, it's 1 foot spacing between the wheels. Every 6 inches a test is being done. So it's very detailed testing. We took simple photogrammetric images just by walking it with an iPhone up on a rod. It was that simple to get the data and stitch it together in the software. Then we overlaid it just to show the background somewhat. And you have to do some transparency to see through it. Then you can start to see conditions underneath it. But it does get to be a bit challenging when you overlay it with this much delamination, in this case, on this particular deck. So for the 5 bridges, detailed reporting was made of course, the measurement percentage and areas for these different bridges. The 24220 bridge I've been showing examples from is the bottom one. The amount of near-surface delamination ranged quite a bit in terms of percentages. This particular deck had a 20.5% delaminated. Top delaminations are called out where there's also possible top delamination in yellow, orange, yellow, cyan, the different colors. Bottom delaminations to see deeper. When you don't have a top delamination, impact echo will penetrate to the bottom of the deck. And check that as well, if there's a bottom steel delamination. And there are certainly bottom steel delaminations. And then finally, deep top delaminations, total tested areas are all called out. And this is where the coring showed 100% correlation, where impact echo, both by NDOT and ourselves, correctly identified the delaminations. So here's an example GPR scan from the ground-coupled GSSI system. It's just showing all the rebar, the variation of cover depth along this scan length. So putting that onto the photogrammetry underlay with 50% data transparency shows the cover depth. And it's going here from nominally about 2 inches up to 6 inches in this color scale. So this is showing your depth of cover, which is an important part of your long-term service life evaluation when you look at chlorides and carbonation and predict remaining service life. So here's the 20% percentile cutoff. Attenuation of the radar signal is what we're looking at, following this ASTM standard to show possible areas of likely potential corrosion. And you can see the attenuation curve here going down in the amplitudes and showing this scattered all over. Now that's, again, on an overlay of the likely corrosion areas. And here's a comparison of the sonic surface scanner, so-called S-cubed, impact echo scanning, with the delaminations and bottom and everything else, with the GPR. I should mention, of course, that the GPR is sensitive to the top steel. You're not seeing the bottom steel in terms of most attenuation studies. It's the top steel that you're looking at, whereas in the impact echo results, that's both top and bottom rebar damage. But there's correlation, but you can see the precision up here is much more than in the radar results, even at this ground-coupled study that we did. So now shifting gears slightly, I thought I would show we have put the wheels occasionally behind a vehicle. And we did this first for a National Center for Asphalt Technology, had a Sharp 2 R06D grant I'll mention in a minute, where we were scanning asphalt for debonding and delamination. But basically what you see here is this was done in the upper Midwest. There were 42 lane miles of interstate highway pavement that were scanned with 2 sets of wheels in the wheel paths, because they were concerned in this jointed concrete pavement, the dowel, they knew they had dowel cracking. So there was cracking where the dowels were, and it extended out further than the dowels in this nominally 12.5 inch thick pavement. So by doing this at 1 mile an hour in the wintertime, we were lucky. We had only 1 snow event in February, but it was there. It stopped us for a while. But we're rolling along nighttime or during the day, depending on traffic control and where we were, literally getting every 6 inches alternating impact echo tests left and right on the 2 sets of wheels. So it amounted to over 2 million tests, but it took us about 10 days to do the project. So it took a while to scan it, for sure, with traffic control. But it was mapped out very accurately, as you'll see. This shows some of the results from that. This is the nominal 12.5 inch thick pavement over this scan length of 520 feet. Here's an example result showing a sound echo of 12.46 inches. Obviously, if you can calibrate to a known thickness with cores, it improves your accuracy, but it was very good. You have to have a speed of sound that you're using for the project. This shows an example result here where there's more dowel damage echoing around plus or minus 6 inches, between 5 to 7. And here's an echo that shows a much higher frequency, 13,000 hertz, 6.2 inches deep. This is at the depth of the dowels. And it was interesting to see in plotting that as you see the wheel paths in the results here, where it's plotted in the red, it extended beyond the dowels. It was associated with the joints, but it was longer than just the dowel length of about 3 feet across the joint. So this all got mapped out for evaluating repair approaches and where it needed to be repaired. And the DOT thought the damage had probably occurred very early in the life of the pavement. Maybe some warping of the slab or something occurred to cause the cracking associated with the dowels. So there are various technologies for assessment of asphalt overlay decks listed here. And I probably have to modify this slide after seeing the presentation on how much bituminous you have done. It's easily the best I'd ever seen also. But nonetheless, it's more sensitive to not being so deep. Impact echo scanning doesn't work well because the asphalt's usually warm. If it's colder and more concrete-like, it can show and test through the asphalt into the concrete as well. But once it gets much above 50 to 80 degrees, it doesn't resonate well. It's very viscoelastic with temperature, much softer, and does not echo well. Whoops, too fast. Okay. My finger's getting too big. Okay, ground penetrating radar is complicated by de-icing salts and moisture. It's often present at the asphalt to concrete interface, so there is debonding. Surface waves. We learned about surface waves and the ability, we've been doing it for a long time. I've been doing non-destructive testing for about 43 years now. And my professor, Ken Stoke, I should give credit where credit is due, and my office mate in 1979 first started researching spectral analysis of surface waves at the University of Texas at Austin when I was in graduate school for the geotechnical program there. So in any case, it was extended to detect concrete delaminations below asphalt overlay decks. We were involved in a study, SHARP 2, at Auburn University by their National Center for Asphalt Technology to look at the delamination of new asphalt pavement lifts or debonding of those lifts. And from that we said, okay, maybe we can extend this to an asphalt overlay deck, and that's what we did. So some of the equipment we make in our subsidiary company, Olson Instruments, the consulting is Olson Engineering, is we have a ruggedized PC. We have these simple hammers, but that's a bar with 2 displacement transducers for doing surface wave testings by hand. And that's a smaller device. I've got one out here at the exhibit that takes this data as well instead of the big PC. So here's a basic result showing time domain records for 2 receivers, a foot apart, 30 centimeters. The big spike is the surface wave energy. So you window in on that and you get phase, and this is very high quality data right here. Phase is just the difference in how fast and the time it takes for the surface wave to travel from the close receiver to the impact to the far receiver of the impact. So having said that, signal coherence near 1 is good data up to about 12,000 hertz. It's wrapped back 0 to minus 180, minus 180 to minus 360. That's one wavelength. And in this case, it was 2.62 feet apart. So velocity equals frequency times wavelength. If you remember freshman physics, anybody? A little shaky? No. You're usually very young if you remember freshman physics. In any case, I did. So, with multiplying it out, it says 6,900 feet per second. That would mean that the compression wave velocity was over 14,000 feet per second, good high quality, high strength concrete where this particular test was done. So from this, you get the dispersion curve. You get velocity versus wavelength, as you're about to see. So we extended it, and this is back early when we hadn't even built a cart for the scanner. We just had a little wagon, the 2 wheels, and the PC, and we drug it along. Well, the wheels are aligned. Instead of being offset 3 inches, so you get left, right, impact echo, you hit on the left to get an impact echo result here, and the surface wave test is done between these 2 aligned transducers. which are typically spaced 6 or 9 inches apart, depending on the thickness of the asphalt. So we did these 2 decks for the Colorado DOT. This shows bonded asphalt on sound concrete. The spikes, the windowing, the velocity versus wavelength. This is 0 to 1 foot going through that deck of a velocity around 5,500 feet per second, roughly, and good data, but bonded, no differences. This shows sound concrete with asphalt debonding. You see a glitch or delay in the phase here that is this drop in velocity from 5,500 to 4,500 feet per second at a wavelength, which is approximately depth of 3.5 inches. That is the debonded asphalt. And that's what you see, this velocity drop. It's not in tight contact. It's a Lamb wave effect, as well as it's just not bonded well, so it's not in tight contact. It's slower at the interface, if you will. This shows a deeper drop in velocity associated with this in the phase. This goes from, again, around 5,700 down to about 4,500. That's at 5.1 inches. That's a top steel concrete delamination. So we can detect that through the asphalt. Finally, here's a bottom delamination where there's 2 drops. There's asphalt debonding at 3.2 inches, followed by a drop at 7.4 inches at the bottom steel, where there's a deck delamination. These are the 2 phase where this is 0 to 50,000 hertz. This is the deeper bottom delamination of the steel. This is the debonding of the asphalt. So what we did, it was an initial blind study, meaning we tested through the asphalt. Then they scraped off the asphalt. They were going to repair the deck. They used hydrodemolition to clean up the steel. And this is our map that we gave them in advance of where we thought it was delaminated from the surface wave results. And you can see in the picture and the scaling, where this is 50 to 70 feet, here's 50, 60, and 70, agreed very well with what we were predicting. And you could see where the concrete was indeed delaminated, cracked up, and broken, and the hydrodemolition removed it as they repaired the deck. So excellent correlation. We've gone on to test well over 30 decks that were asphalt overlaid with good results with coring and other things to confirm it. So there's just a quick summary. The impact echo scanning being the most accurate in terms of the Purdue and NDOT research. It identified bottom delaminations as well as getting the deck thickness. Surface waves was found to be good for mapping out delaminations of asphalt overlaid decks at asphalt pavement lift debonding. The scanning mapped out the horizontal cracking damage in the jointed concrete pavement associated with dowels for 42 lane miles of the interstate. And data fusion was useful to overlay the results. So I have to quickly finish because I'm conscious we have to get to a coffee break by 9:45. So in any case, this is a little different approach, but similar technologies. So we did a rather unique concrete bridge girder study on an older bridge in the eastern United States over salt water with de-icing salts. So it's a really unique bridge. We did 3D radar to detect embedded reinforcing post-tensioning ducts and steel plates, as well as pre-stress. There was pre-stress and post-tensioning in this old bridge. Surface waves was used for the cracking extent, the depth of perpendicular cracks. Impact echo scanning was done to check for voided versus grouted ducts at the joints, and it all was overlaid with data fusion on photogrammetric images. So here's the digital photogrammetry. It's just laid out. We laid out a 6-inch grid on this joint. This is actually a cantilevered girder on this side, a drop-in middle span that's also post-tensioned to another cantilevered girder. It's a really unique old bridge. So it's 20 inches thick right at the joint and more like 7.5 to 10 inches thick in the webs as you move away from the joint. So there you see the image, very detailed. Nice presentation yesterday on photogrammetry. But the physical principles of radar, you can go to this ASTM standard. Basically, as you move along, it reflects from changes in dielectric constant, meaning the steel stands out very strongly because it's conductive. And it is very excellent for mapping steel. So as you move along, transmitting and receiving, structural radar is like 1.6 gigahertz to 3 gigahertz typically. higher frequencies. The corrosion shows up by a lower amplitude reflection, kind of a fuzzy reflector, but it's lower amplitude. So if you have a corroded rebar versus a non-corroded rebar, the basic physics means this is a weaker signal. So here we are scanning in two directions with the GSSI Miniscan XT unit, Structure Scan Mini XT, 2700 megahertz antenna. You see the results on screen. It's very nice. We went at a 3-inch grid both directions because we wanted to image it. So we're doing kind of a tomographic analysis. Basic processing with 2D radar shows the unprocessed scan. Deeper tendons have a broader hyperbolic shaped reflector versus the shallower rebar. And this is depth and this is distance scan, that's 5 feet. You can migrate it, collapse it into the shapes of these hyperbolas, becoming both the deeper tendons and the rebars. And finally, a Hilbert transform can enhance the viewing of that a bit more in terms of the images. So when you take all this together and combine it, this is what I mean about it being complex. They had shop drawings, but they weren't, well, they were either kind of design drawings. They thought they probably built it this way, but they wanted to check it and see, was it built that way? Because they wanted to get another 5 years out of the bridge before they replaced it if they could by repairing it. So in any case, this is an embedded steel plate. This is an embedded steel plates. Here's a small one. You can see it with somewhat clarity, but I wouldn't say it's perfect, but you can see where the shapes are. This is certainly some angled stirrups and rebar. These in the webs, it's easier to see there, are the post-tension ducts are showing up over here. And so all of this was put together in a radar sense to image it and check it. And it pretty much confirmed it was built as they thought it was built. So we also did surface waves across cracks to see how deep they were. And it's up to 20 inches thick when you're right on the thickest part of the joint. And so it was hit in line with this to get the results. And we saw results of velocity versus wavelength. This is velocity, around 7,500, 7,000 feet per second. The drops in velocity is showing from 4 to 8 inches. This here is across the crack, showing it's about 7 to 8 inches deep from the surface, and then the velocity increases. That's typical of what happens around a crack. It gets slower until you're beyond it. And this is a more normal result where it was in the web and it was not so very thick, only 7.5 inches thick when the velocity drops as you get it out of the web. So we took that data. Then we did impact echo. Obviously a problem in post-tension bridges is voided versus grouted ducts and the corrosion of the strand in the long term. So we came up with years ago, I was sitting on an airplane when I thought of this idea after doing endless point-by-point testing. I said, we've got to be able to scan. So the impact echo scanning idea was born because of tedium of testing forever. So it ended up being this system. We've sold a lot of these, interestingly enough, to China because we used to sell a lot to China. They're not as popular now. We recently sold another one. I think there's some political issues going on. But they were doing a lot of post-tension bridges, and they used a lot of quality assurance of voided versus grouted ducts on new bridges. So in any case, it's spring-loaded. It was the progenitor, if you will, of the bridge deck scanner, the sonic surface scanner system. It's spring-loaded with a sensor every 1 inch. You push it along. You have a choice of a larger solenoid or a smaller solenoid, and it impacts every 1 inch as you scan. We had a research girder donated to us. We did radar on it. We were so lucky to get our research girder donated. They were not lucky. They blew the drape of the ducts. It was junk to them. So we said, okay, can you donate this $50,000 girder to us? And by the way, please leave it in your yard. We can't put it at our office. They did. So we had a contractor grout them, created defects with styrofoam void. This was an NCHRP study as well. Basic physics, when it's fully grouted, it said it was about 11 inches thick. It looked thicker when an empty duct because there's a hole in it. It's going to resonate at a lower frequency. The basic indicator of a voided versus grouted duct, or honeycomb. Could be honeycomb, but in this case it was voided versus grouted ducts. So we plotted that all up in a color scale, going from the normal thickness of 11 into the reds and whites, much thicker. This shows what the void that was built and how it looked in the results. You can look at that in a skewed sense and see over this 20-foot length that we used of where it was more voided, and it agreed very well. So on the old bridge girder project, we scanned a number of girders vertically on a 6-inch grid, pushing it up the wall. Here was a sound result. Well-grouted ducts, 7.5-inch echo thickness in the web. This, on the other hand, showed a nominally 8 to 9-inch thickness on this web, but it increased to 12 inches where there was an ungrouted duct. So we could identify that. And that correlated because we knew from the radar there's a duct there. So we put that all together, again, fusing it all, showing the impact echo areas of questionable or poor grout in these color scales, into surface wave crack tip depths on this color scale from 2 inches to 10 inches, and also showing the radar results as to where the ducts were located. Here's right at the joint. Those were web plots there, right at the thicker joint of 20 inches, and we did do radar from both sides on this to cover it well. But again, you can see all the results from the impact echo scanning, as well as the surface wave testing across it in that regard. So I think I actually got to the end of my talk about right on time. Thank you very much for your time and attention. I pushed a little today to get through it. I hope you enjoyed it and learned something, and be happy to answer any questions or run the scanner outside at the break.